Welcome. In this particular lecture we're going to have a look at how we, particularly within a managed language like Java or C#, how we can create code that isn't inefficient. So a few hints and tips or sort of good guidelines by way of creating code that's okay. We'll also have a look more generally at optimization in terms of what it is about, when it is appropriate. So we'll start off having actually a look at the importance of optimization and how this fits into not only to games really, but basically all apps or programs that we may want to create. Optimization, if we were to define it, it is all about creating your program so that it uses the minimum amount of some resource. Now that resource could be CPU time, it could be memory, it could be network traffic. So it's trying to make it about minimizing the amount of needed resource for your program. Quite often, or I suppose the default assumption we're thinking about optimization, it is in terms of the CPU time. So to try to minimize the amount of CPU effort that's required to do something, which means that then runs quicker and faster. There's two areas or aspects that optimization can focus on. One is in terms of the design, and this is looking at the choice of algorithms, but the choice of data structures, and having the setup that's right that makes it as efficient as possible. The other form of optimization is in terms of how it is coded, the implementation, and this would be in terms of the particular language features that are used, the structures, how that will get to be compiled and get to be executed. For this particular lecture, we're mostly concerned about code optimization and not so much in terms of the design optimization, though we'll talk about it briefly. When we're thinking about optimization, there's a few general guidelines. First of all, design optimization is good. This is generally the area where the large performance gains arises. And certainly when you're thinking about the design of your program, you do want to think about and to ponder the performance implications or the performance challenges or bottlenecks that you're going to be facing, and think about how can you make your design efficient. And that's generally always a good thing to put into your particular development, a good design optimized to be efficient. For code optimization, the general advice is don't do it unless you really need to do it. You should be writing, not inefficient code, but okay code, well designed, well defined code. But you shouldn't go out of your way to optimize the code that you write to make it highly efficient, unless you really need to do that. So general advice is don't optimize code in earnest until there's a real need for that to happen. And there's a quote here by Professor Tony Hoare. We should forget about small efficiencies, say about 97% of the time. Premature optimization is the root of all evil. So only put it in when it's really needed. As to the process, and let's assume that we've got a game, we've got a target number of updates per second, and that's what we're aiming for by way of having a nice playable game. But when we run our game and we measure how many, say, updates per second we're getting, we're realizing that we're falling short of our target. What we do in that case then is to profile the game, is actually to look at, be it instrumentation or another technique that sort of measures how long you're spending in each method, how many times you're calling each method. And that gives you a way of finding out, well, where the bottlenecks are within your particular process. Based on the profiling, and it's important actually to approach this, scientific's the wrong word, but not simply to guess where it's too slow, but actually to measure and to time and to see where it is slow. Based on the profiling, that will give you useful information, and you can then think about how you can go about changing your code, tweaking those aspects to try to optimize it to improve the performance. Once you've done that, fair enough, you implement whatever optimizations you've planned. You run it, you measure to see what performance increase there has been, And in essence, you repeat that process until you've hit your target again or exceeded your target. Worst case, if you can't hit your target, so you've tried all the optimization you can do, but it doesn't matter how you change the code, you're still under your target number of updates per second. It's a more significant issue. You're either then going back to your design and thinking about, well, how do we change our design to improve upon things here? Or you're looking at the feature set and thinking, well, do we have to cut back on some of these features? But ultimately, you know, if you can't hit your target, you need to do something about that. For managed languages, Java, C#, they compile to an intermediate language, and then they are turned into executable code from the platform that you're doing at runtime. A lot of the Java environments will use a just-in-time compiler. So they'll take the intermediate language, they'll turn it into assembly at runtime, so effectively it's compiled really at runtime. The compiler, and a good compiler, will help us. It will actually look to see how it can run our code faster. And when we have a look at C++ later in the module, you'll see that C++ compilers, there's loads of optimizations that they can do. But that's not just done in time, rather it can be done, it can take as long as you want for C++. Here we are taking our Java at runtime and doing the compilation. So the range of optimizations is a bit more limited. But a good just-in-time compiler, it'll do things like constant folding or method inlining. It'll tweak our code so that if we're calling a small method frequently, it'll just put in the method code. For extraction of loop invariants, if there's a piece of the loop that never changes but we're repeatedly doing it, a good just-in-time compiler will bring that out of the loop, so only do it once, and so on. So there's lots of small optimizations that a good just-in-time compiler can potentially put in. The side at the bottom really refers to the Android framework, that there's a lot of variation on Android, and on some platforms actually there may not actually be a just-in-time compiler, so you are somewhat at the mercy of the platform that you are deploying to. Now, the cost of optimization. Now, the obvious benefit of optimization is it runs faster. You generally don't get things for free, so the cost of optimization, you can see a number of examples here. Some of the risks, some of the costs, is that it could potentially break code that works, that you could optimize it. You could optimize it in a way that a part of it runs faster, but maybe you've broken it for some other conditions, and you need to be careful that you fully retest all of the optimizations. Potentially also limits the reusability or extensibility. One of the common optimization techniques is that you assume certain things are going to be true, and if they are true, then it enables you to put in shortcuts or more efficient ways of doing things. Often that means you're going from a generic solution down to a more specific solution, and in doing that, obviously you're limiting the reusability, the flexibility of it. Another common cost of optimization, certainly at the code level, is that often you're changing things in a way that makes the code base more difficult to understand or more difficult to maintain. So generally it lowers maintainability too. The bit at the bottom, the important bit, it is truly important. I'm talking here about optimization where you are going out of your way to change the code to make it run as fast as is possible. I'm not talking about writing code in a sort of a standard way and making sure you're writing it in a sensible way that isn't inefficient. So there's a whole spectrum here, but this is very much about the cost of pushing it out towards full optimization. That is not to say you shouldn't be concerned about this, and you said relevance. It is very important that you do actually write code that isn't inefficient, but you don't always have to write it so that it is optimally efficient. Why does this count? I mean, obviously in a game where you have, you want to try to make this impressive as possible, and it can put large demands on the CPU and GPU, efficiency matters, but actually it matters for everything. It doesn't matter if I have sort of a scheduling program. If it's efficient, if it runs fast, it means it's more responsive. It's going to be a more responsive interface for the user. It means that I'm putting less demand upon the CPU. And ultimately, in a mobile device, in a tablet and a phone, that means the battery life actually gets to be improved because I'm draining it less through the load in the CPU. So no matter what we're writing, efficiency matters. It is a key, crucial component to making sure that we have good battery life within our devices. So having introduced the notion of optimization, having said it's important, but there are costs associated with it, let's have a look at some rules of thumb. Now these are not hardcore optimization techniques. These fit into the middle ground. They're ways about writing code that is easy to do, is generally applicable, and will avoid situations where you introduce performance penalties. So this is very much sort of the middle of the road, good coding standards. And we'll look off first of all at how we ought to create objects. What we can have to acknowledge and to recognize first of all is anytime you say you want to have a new object of some type, that's operation isn't free. Creating an object is a fairly expensive thing to do. You have to construct it, and when we think about constructing an object, it means that the virtual machine has to go away and actually to allocate out and reserve sufficient memory for whatever properties or class values you've defined in your object. It then has to initialize that to zero that memory. It then has to go to the constructor, and you may have multiple constructors as a superclass, and to execute whatever code that they have by way of giving it initial values or initial setup. So all of that takes time. It is a cost, and often it's quite a high cost. So for hints and tips, and generally these are ways of avoiding that particular cost or minimizing it. Java, C#, you have what are known as wrapper types. So we have an int, an int. That's a primitive piece of data. It's not an object. It's just simply a small chunk of memory, normally 4 bytes, that sits in the stack. That's very, very fast to create. We just allocate a little bit, no constructors involved, very easy to get rid of. But you also have integer classes, and these are proper objects. In both cases we can use them for storing numbers, but we should virtually always favour using the primitive data types as opposed to the class-based wrappers. Lazy object creation. So we should avoid creating objects if we're not actually going to use them. And if you look at the example in the middle of lines 1, 2 and 3, here we create a string message. So there's a cost in creating a string which is an object. And we've got a condition, if we're going to print the message, then we print it out. The problem with this is that presumably sometimes the if isn't going to be true. So we will actually create and delete an object for no purpose or no effect whatsoever. So we're using lazy object creation, that we will only create the object whenever we actually need that particular object. And you see that in the example there, the middle example shown on the screen at the minute. For string literals, strings are objects, but they're very frequently used. So a literal, the strings are immutable. You can't change them. Anytime you want to change the content of a string, you actually create a new string. And if you look at the 2 examples here at the top, we're saying string 1 is equal to the string hello. And that's a literal value. It doesn't say give me a new string. It just says it is a literal. It seems like the number 4. This is the literal string hello. Whereas in the bottom example, we are creating a new string which happens to contain the literal hello. The advantage of the top implementation is that most managed languages will maintain a table of all of the string literals that have been used. So if we want to access one of those string literals, we do it directly by reference. It's quite fast. Whereas the example on the bottom, we actually will go to the effort of creating an entirely new object, which happens to contain the string hello, so it's a much more wasteful implementation. Garbage collection. This looks at, well, what happens when we finished using our objects. They have to be good of scope. Those objects then are not needed. They have to be released, and that's the process of garbage collection. It will go through, it'll free up the memory associated with that object, it'll make sure that we sort of clean things up and memory's left in a nice tidy state. One of the big strengths of many languages like Java and C# is that the programmer doesn't have to worry about this. It is done behind, well, they do have to worry, but they don't have to do it themselves. It's done behind the scenes for them. When we look at C++, it isn't. It's something the programmer is going to have to be responsible for doing. Now, whilst we, as Java programmers, don't do this, we shouldn't forget that it is quite a large undertaking to manage this memory. So whilst we're not bothered about it in terms of effort we're putting in, we should be bothered about it in terms of the demand that is putting, for example, on the CPU. And ideally, we want to minimize the amount of strain that the garbage collector introduces. For a game, there's a few key things that we want to look like. Is how long does the garbage collector take? Now, garbage collector is generally run as a thread in the background, runs alongside all of your main game threads. And what it's looking for is a quiet period where it can jump into action, go through memory, look to see where you have effectively dead objects that have been discarded, clear up their memory, piece things together. And it does look for a quiet period, but it also will trigger and jump in periodically if it doesn't find a quiet period. Garbage collector is a question of how long it's going to take to run. It might take 40 milliseconds, and if you're doing a sort of normal user-based interface, 40 milliseconds wouldn't bother you in the slightest. From the perspective of a game, though, 40 milliseconds could be a couple of frames. And if we're being paused for a couple of frames because the garbage collector's leapt in, we actually could have a small skip in our frame rate. It can potentially be noticeable, and on a regular interval you might see a small skip happening. So we need to be concerned about, well, how long is it going to take to do, and also how frequently is it actually going to be running. If they are large collections every few seconds, then we are likely to see a frame being skipped every few seconds. Conversely, and you can sort of configure sometimes how garbage collectors actually, how frequently they run. If it runs very frequently, there may not be a heavy cost associated with it, but there's a bit of overhead then, so you're just not being as efficient as you possibly could be. General advice, and this refers to objects, it refers to limiting the load in the garbage collector. General advice is very simple. Don't create new objects unless you really, really need to. So avoid creating objects. If you do need to create them, think to see, well, can I reuse some existing object? Does it really have to be a new, entirely new object? Can't I reuse something? And a few common ways of looking at reuse is to use an object pool. So this is basically a container class which stores a pool of objects, and other objects can sort of ask to get one of the stored objects from the pool. They can use it and then they can return it back into it. Alternatively, you can recycle and reuse objects. So if I have a method where, for example, it's my update, and I'm doing something very, very frequently, I probably don't want to create an object every single time I go into the update, simply to use it there and then to discard it. I could create it once, for example, outside of the object. It could be a private property of the class, and then I just keep reusing that single object within the update method. The last one is what we've already mentioned about so far, is use lazy instantiation. So wait until I really, really need to use that object, particularly if it's conditional that I may not need to use it, before actually incurring the cost of creating the object. Next up, we're going to have a look at calling methods and some of the ways we can optimize this. So a small fragment shown over, or two fragments on the right hand side. The one at the top, if you look at the for loop in line 3, what we're doing, we're accumulating the length of strings to some meaningless operation. But we're iterating it from the string. Starting from the beginning, I is going to be the sort of the character index here, and we're doing this up until we reach the length of the string. So string object dot length, and then just doing our normal increment. Potential disadvantage of this, and this will depend upon the quality of your just-in-time compiler. It is possible that every single time we go through that for loop, the string object dot length will be calculated every single time. Even though it's invariant, it doesn't change. That means that we could have multiple calls to that particular method. And again, when you call a method, there's a cost involved in actually setting up the parameters, branching out to it, letting it execute, coming back. So calling methods, not as heavy a cost as creating an object, but nonetheless there's a cost to it. The example we see in the bottom is where we are saying that string object.length, it is known as a loop invariant. It doesn't change within this particular loop. We know it's going to be the same. So we've brought that out onto line 3 in the bottom, where we're calculating it once, and then we're using that calculated value as part of our loop iterations. Now, a good just-in-time compiler, a good compiler would be able to recognize that, though you are at the mercy of the compiler being able to do this for you. Little aside at the bottom, I mean, if you actually think about what's being calculated here, it's just an inefficient way of calculating it. You could just calculate it directly. Other examples about how we can improve our method usage, they're all along similar lines. You can see another example here. We're going to enemies. We're getting out the ith enemy, and we're asking, is it alive, it is a boss, and triggering some action based on that. Because we're reusing that, it makes sense to pull the thing out of the collection once and then query whatever methods we need to query on it. Related to methods is the notion of chalky or chunky method calls. And chunky call is a method call when we call it does several different things, whereas chatty call is one where we call it only as a little bit, and then have to call another method to do another little bit, another method to do another little bit. And generally, for processes that run multiple times per second, these tend to be update and draw. We want to avoid chatty methods, sort of to combine things into a chunky call. So we call it once and does several things as part of that single call. Makes it a little bit more efficient. Next up is boxing and unboxing. And when we mention boxing, what we mean here is taking a primitive value, like an int, and wrapping it up within, for example, an integer. So you can use the integer class to box the underlying primitive, the int. Unboxing is the process of taking that int out of the integer. And in some cases, boxing and unboxing, it can occur implicitly. It's done behind the scenes on your behalf. Generally, boxing or unboxing, they are what you definitely want to avoid them. They are quite expensive operations. For boxing, we might take our int, which is sitting on the stack. We have to actually go and then create a new object living on the heap, and we'll look more at stack and heap when we go into C++. Populate it, maintain a reference. For unboxing, we've got to take it out, we've got to discard that temporary object that was created. So it's quite inefficient to do this indirect manipulation. It is very computationally expensive, it could be an order of magnitude slower, so generally we want to avoid these. How do you avoid it? Make sure we're not using data structures that accept general objects. So for the collections, for a lot of the collections, you can confine, for example, your array list to ints. If you just had an array list on its own where it accepts any type of object, then an int would be boxed as an integer when you're pushing into it. So always make sure you're casting your data types to be explicit on the type of data that they hold. Now I have a little bit of general advice on data structures. And that general advice is that if the size of the data is fixed, then favor using an array over, for example, an array list. If the size of the data isn't fixed, can change, you get a couple of options. You can use an array list, or you can use a linked list. Both of them sort of provide growable, dynamically growable, changeable arrays. Which one should you prefer? If you're not going to be adding a lot of values, particularly to the middle, sort of inserting values or deleting values from the middle, but you're likely though to be jumping over the data, maybe accessing the second value, then jumping to the 8th value and jumping back to the 3rd value, then an array list is the appropriate data structure. If, however, you will be frequently adding and moving things from the middle or the start to the end, then a linked list is a good choice. The linked list isn't a good one if you do need to randomly jump from different positions within it. What happens if you need a data structure where you want to have random access to be able to easily access any position, and you want to be able to add and remove things again from the middle quite frequently? You're kind of stuck at that point. There is no one data structure which is fast for all of these things. Well, arguably there are some ways of doing it, but quite dangerous in terms of memory. In that case, you're sort of looking and picking one of them and asking, okay, what's more important? Is it more important that I be able to quickly access the values, or is it more important that I'm able to quickly add and remove values from it? Other aspect we have is using a hash map or a hash tree map. This is where we want to store object pairings. So we have an object and we want to have a key referred to and linking to that particular value. So we use a hash map, we can use a tree map for that type of linkage. We should favor a hash map if we don't need to iterate over these objects in any particular order. We just want to pull them out by their name. Then a hash map's good for that. If, however, it is important, to be able to pull them out by name, but also to iterate over, say, the order added from the start to the end, then a tree map is the appropriate data structure to use in that particular case. Key takeaways in this, by using a few, and there are not too many guidelines here, using a few simple guidelines, you can write code that maybe it's not going to be optimal in terms of the highest possible performance, but it will not be inefficient. It will be decent, good performance. And that's what we want to aim for. We want to make sure we're writing things not to be highly optimized, but just to be decent performance. We certainly want to avoid things which are inefficient. And the largest risk that we face is actually creating unnecessary objects. If we do actually find ourselves in a position where we've written code well up front, but it's not running as fast as we need, then it is necessary at that point to look at, okay, well, what can we do to optimally improve the performance, to make it run as fast as it possibly can run. But remember, there is a heavy cost in terms of time, effort, and potential impact onto the code in terms of the maintainability, extensibility. So you don't want to go there unless you really, really need to introduce that into it.